right, everyone. Welcome, welcome. We're going to go ahead and get started. I want to thank everyone who is joining us. We have a few quick announcements that I want to give you all. First, we are recording this session and it will be available in Whova, our conference app, within 2 weeks after the Congress ends. If you would like to ask our speakers any questions during this session, please use the Q&A area to the right of your screen. The chat window is where you can engage with other speakers as well. And we kindly ask that if you could keep your microphone and your camera off during this presentation and follow the presenter's lead on when to engage with cameras or your microphones on and off. So that is all I have. We're going to go ahead and get started, and I'm going to hand it over to Nick to get us started.
All right. Hello, Affy. How's everyone doing? Thanks for coming to our session. So the focus of our session today is on post-fire ecosystem recovery. One of the things I just wanted to mention quick to kind of set the stage is that climate change is going to be a huge focus for our session and likely most other sessions here this week. And I just wanted to note that, the thing is, we're no longer talking about future climate change. The future is now, and we're living in a different world than most of us grew up in. And as researchers, we have this unique seat in history as some of the first to kind of document these changes and begin to understand how ecosystems are adapting to these new conditions at local, regional, and global scales. And to work off the theme of the conference, we as a people, we're going to be living with and be impacted by a world with much more fire. And as scientists and practitioners, we're going to need to learn to operate under these novel conditions and to identify prescriptions for enhancing the resilience of our natural systems. And we know that we can make a difference because we've been doing it. Indigenous peoples have been doing this for thousands of years on our landscapes. So to start off our session here, Andrew Larson is going to be talking about his research along those lines.
Thanks, Nick, and hello, everyone. I'm just going to get my PowerPoint up, and we'll get going here. Okay. Can I get a confirmation that you're seeing what you should be seeing?
Click the slideshow again.
Resume slideshow. How's that?
No.
Okay, let me try again. We're on.
It just worked.
It did. Maybe try that. How's that? Resume slideshow. You see it now?
Yep, we're good. Yep.
All right, great. Although I don't know. Wow. There, is it working now? Okay, sorry about that. We tested the tech, but here we go. Okay, so I want to quickly recognize all my co-authors. So my name is Andrew Larson from the University of Montana in Missoula. And what I'm presenting this morning is basically a synthesis talk that is based on a new paper that the group of co-authors here that you see on the slide have out just this week in Forest Ecology and Management. And I'll pop a link to that paper into the chat, and maybe Nick can get it onto Whova at the end of the talk. But basically, this is about, I'm going to present a framework, basically a principles-based approach and an analytical framework for thinking about fire effects and post-fire management. And so a little bit to set up sort of the problem, I guess, the motivation for this. And these are sort of things that we already know, but I want to work through them. So first of all, like if we look across a region like the Northern Rockies, where I'm based, there's an obvious scale mismatch between the work that we're accomplishing on an annual basis through prescribed fire and mechanical treatments and what wildfires accomplishing across the landscape. It's 1 to 2 orders of magnitude in any given year, larger area impacted or visited by wildfire. So we've got a fundamental scale mismatch going on. Another point that I'll make to sort of start this out is that wildfires seem to frequently provoke sort of a strong sort of philosophical or perspective shift in terms of how we are approaching management and management objectives. And it's not uncommon in individual planning areas, say a big NEPA project area, to have sort of an approach that's informed by ecological principles and carefully planned in a green pre-fire landscape setting. But then a lot of that often seems to go out the window when we move to the post-fire, like when there's a random wildfire event that burns through, for example, a project area that's just about made it through NEPA and it's about to go to implementation. And you know what we often find ourselves with is sort of a situation that looks like basically we've abandoned many of the ecological principles that were guiding that green forest work, and now we're focused appropriately on short-term mitigation measures, but then oftentimes transitioning to basically looking for salvage opportunities, and maybe in the years down the road looking for places where we might need or want to do some planting. And then a third sort of motivating factor, and Nick spoke to this at the outset, is that climate change is really forcing a paradigm shift on us, where we're not so much thinking or talking about restoration anymore. It's more about adaptation. And so, you know, you go to a landscape like this, where the day before the fire started, you could stand at this vantage point and might be having a conversation about restoration and what we're going to do in this landscape to sort of restore things. But after the fire, and given the fact that post-fire development is occurring in a different environment climatically than the pre-fire community developed, just fundamentally changes this, whether we like it or not, to a perspective on adaptation. And so what all this sort of sets up is the need that we're trying to fill with this paper for some principles to help guide development of ecologically based post-fire management, and an analytical and planning framework to help decide where across large bird landscapes we might want to do management. So I'm going to start with the principles piece and work through these quickly because, you know, they're pretty foundational. You know, principle one, you know, we're going to protect large diameter trees and fire refugia. And I'll start with the big trees. And basically, this principle is about protecting the things that become rare and that are hard to replace and are providing essential ecosystem functions in the burned landscape. There we go. And so the big trees are doing all the things that we know big trees do, including the big dead wood. So it's not just about the live green trees. And then fire refugia. So without sort of splitting hairs over definitions of fire refugia, recognizing that the residual unburned patches in that landscape provide essential functions that for a period of time are going to be particularly rare and maybe particularly impactful. So principle two, this is I think a big one in thinking about, okay, where's this landscape going in the near term future? And you know, the fact is that first entry fires create fuels on a 5 to 10 year time horizon, especially after a long fire free period. And these may be areas where we're going to want to focus for post-fire treatment, especially in either frequent fire or historically frequent fire sites that were fire excluded, or places that are now transitioning from a long interval to a short interval fire regime. Now, hand in hand with that, one of the key principles here is to identify places on the landscape where the wildfire has either reinitiated or created opportunities to reinitiate and maintain stabilizing feedbacks. So, you know, you can see that a lot of this is going to be identifying places where the fires interacted with recent prior fires or recent prior management to moderate the fire effects. And these really can become anchor points and opportunity zones, I'll call them, across the landscape post-fire. A key thing, especially in the high severity parts of the landscape, is to differentiate between climate and dispersal mediated transitions to non-forest. So you look across the landscape like this, you say, okay, where across much of this landscape, it's not going to, I would expect, I think most of us expect that we might have some difficulties with post-fire tree regeneration. but figuring out how we might manage this landscape with respect to that requires an understanding of, where is tree regeneration basically precluded by climate going forward, and where is it dispersal limited? Because that's something that we can influence with management. And then finally, principle 5, looking ahead again now. So after the fire, what work remains to be done to align species composition and structure with the anticipated climate and fire regimes going forward? And so that might look like assessing seed sources and trying to identify, are there mismatches with post-fire climate or absences that we want to address? And there also might be, I'll call it sort of cleanup work, where places where fire didn't do as much as we'd like to have done. And so, are there places where we want to follow fire with additional work? So 5 principles, and I seem to have lost, there we go. I'm back. I keep switching between screens here. 5 principles to begin to guide our thinking about, what does the state of our ecological knowledge tell us about the types of things we want to prioritize and do in post-fire landscapes. What we need to address now is the question of where across the landscape. And that's informed by large landscape evaluations and departure analyses. And basically, this is a data-driven approach to characterizing post-fire landscapes. We take a large view, organized and constrained at water scale levels or watershed scales, and includes some sort of a departure analysis. Lots of ways to go about doing that, but critically, that departure analysis needs to not just look at historical range of variability, but needs to, as much as possible, look to the future. And the point here is to use that sort of a reference to understand and identify, patch types or conditions that are over or under abundant, or issues with landscape pattern that might become problematic, fragmentation or coarsening of the grain with giant uncharacteristic patches, for example. So with the rest of the time, I want to work through a couple of quick examples taken out of the paper. These are 2 recently burned watersheds in north central and northeastern Washington, Benson Creek and Statter Creek. And here, the top row here shows projected future climatic water deficit. And so this integrates the regional climate and climate change projections with the topographic template. And then it's been binned up into course classes that are relevant to the types of vegetation that are expected to persist there. And then the bottom row, you can see the burn footprint and severity information. So the first key step is to get a snapshot of how fire has updated and edited the landscape, the changes in forest structure. And you can see the top row here is showing, in this case, photo interpreted structure. The details are in Derek Churchill's companion paper. And the bottom row is an updated assessment characterization of landscape structure and forest structure classes using the same methodology after fire. So there are lots of different data sources and technologies that one could use to accomplish this. This project used aerial photo interpretation. And through the departure analysis, it gives us a way to identify and characterize the major changes and to put them in the context of HRV and FRV. So we look at Benson Creek, this was an extreme fire event. It burned with very high severity, created some huge open patches. When we look at that patch size distribution relative to HRV and FRV, it's really been coarsened. And not surprisingly, the large and medium tree structure classes are now really low relative to both HRV and FRV. If we go across to Scatter Creek, our other example case, here, the landscape was already pretty fragmented by past harvest, which had also depleted the large trees. And then this fire event, burned at relatively low severity, and it actually had the effect of further increasing fragmentation. You can see that in the post-fire structure picture below. And we recognize that we're low in the large tree structure classes, both open and closed canopy across this landscape. So we've got a framework now for thinking about some high-level prescription or some guiding principles a large landscape approach to characterizing pattern and fire effects, but what do we do with this information? And this is where we really begin to synthesize these ideas with actual data and analyses to try to step through an analytical process to make sense of our post-fire landscape. And what we have in this talk and in this paper is an approach where the post-fire patches identified on the landscape based on the data that I've already showed you, as well as critically treatment history and past fire history, are allocated or classified sequentially into 7 different potential categories. And the first are the climate limited patches. So these are places that burned at high severity, and they also are in an environment that we don't expect to support trees in the future, at least it's unlikely. After that, we're going to try to identify the dispersal limited environments. So these are high severity patches that are far from any residual seed sources, but that are on sites that are expected to remain forest capable going forward. After that, we want to classify out structurally complex patches. So these are closed canopy patches that are growing in environments that we expect them to persist. We want to identify stabilizing feedback patches. So these are places on the landscape that the most recent fire interacted with recent past fires and treatments. 2 related categories. So these are places where the post-fire structure or composition is not well aligned with either the current or the future climate or fire regimes. And then once you've made it all the way through this filtering process, everything else that's left over we call resilient structure. So what this generates then is basically a spatial landscape prescription, a classification of our post-fire landscape where different types of actions are more or less appropriate. And this gives us a way to make some sort of begin to prioritize the types of actions and their locations across the landscape. And so Benton Creek here, one of the obvious things that falls out is we want to avoid the climate limited places, focus our reforestation efforts in the dispersal limited patches, and even within there, focus on the environments that are likely to support trees going forward. The other thing that comes out of this is that the notion that one of the things to do in this watershed might be to do preemptive green treatments in the unburned portion in the southeast and south central part of the watershed to maintain the large trees that are still present in this burned landscape. If we go over to Scatter Creek, Nick's giving me the stop sign. We can apply that same thing there. So I'll just wind up here with my conclusion slide. The hope from this is that when we take a principles-based approach in a large landscape view, that we can basically shift the dialogue and take a more proactive and almost sort of partnership approach, I'll call it, with wildfires to adapt our forest landscapes to future conditions. Thanks.
Thanks, Andrew. Very good.
Yes.
Okay, next up is Alina Cansler from the University of Washington. Go ahead, Alina.
Hi, folks. Welcome to my talk and welcome to the AFE meeting. I am going to be building on the talk that Andrew just gave, talking about using remote sensing at 2 different scales to evaluate the impacts of both past fire history, so fire and fire interactions, and post-fire silvicultural or fuels management on forest in northeastern Washington state. And I am presenting to you from Missoula, Montana, land of the Salish, but I am affiliated with the Forest Resilience Lab at the Precision Forestry Cooperative within the University of Washington. And let's see if I can get my presentation to go forward. There we go. This body of work that I'm presenting was part of what we call the Northeastern Wildfire Project. And this was funded by the Joint Fire Science Program with a science team of a number of scientists from University of Washington, Washington DNR, Utah State, and University of Montana, and the Forest Service. And we've got 5 manuscripts out of this. You've already heard about one from Andrew Larson. You'll hear another one, more about this research later in the session. And I'm going to be covering 2 of them that I led that just got published in Forest Ecology and Management. And the links are in the Whova chat if you're interested in seeing those. All this work is done under the broad umbrella of understanding when and where fires are restoring landscapes or altering the trajectory of landscapes. So where have they done beneficial work that can be moved along further, or where did they overshoot and there might be a need for correction? Specifically in this talk, we're interested in exploring under what conditions do previous fires limit high severity in subsequent fires. So not where they're limiting the spread, but where they're limiting the severity. And we looked at that using severity data from the Landsat satellite platform. And then the second part of the talk, I'm going to be looking at the impacts of post-fire management on forest canopy structure using 4 different treatment combinations. And we're looking at forest structure using aerial light lidar data, which I'll describe in more detail. Just to give you a setting in the world, here we are. This is the west coast of North America, and we are in Washington State, and we're east of the Cascade Crest in the North Cascades Ecological subsection in the Okanagan Highland Ecological subsection. These are areas with steep, complex topography. That's part of why they're near and dear to my heart. And they're areas with really varied conifer forests in terms of species composition and structure because of those steep elevational gradients. And we've got, on the right, if you can see here, the lighter colors are lower elevation forests that kind of match up to this dry mixed conifer. These are places where indigenous land management practices kept fire frequently on the landscape historically, and the colonial system interrupted that by removing of indigenous burning and grazing, selective harvesting, as well as fire suppression eventually. But then we also have areas where the forests are cold, fires are infrequent, patch sizes are large. And just to give you an idea of what this landscape looks like, it is complex, and you can go from moist forest and dry forest all the way up to high elevation forest in a really short amount of area, short of distance. So to look at burn severity across this landscape, we compiled a burn severity atlas using Landsat satellite data, and we used Google Earth Engine to process every fire that we had perimeter data for from 1985 to 2019. This resulted in an atlas of 437 fires. This included some very small fires, but including them let us get at multiple fire interactions, so reburns, where fires have burned 2 times. I'm focusing on the reburns in this talk. If you want to know about initial fire severity, I'll direct you to the paper. We had 65 reburns that I used in this analysis that occurred between 2002 and 2019. We used those later years because that's when we had day of burning data available from MODIS satellite data, which would let us get to fire weather during the day of burning. We sampled those fires on a 270 meter grid for predictive modeling. What we were trying to predict was the burn severity, classified into unburned, moderate, or high. I'm focusing on the high right here. And to predict it, we used a subset of set of variables that we know relate to drivers of fire behavior. Specifically, the weather during the year, during the days the fire was burning, and the annual climate variation anomalies leading up to the fire, as well as data on the bioclimatic setting, specifically related to the fire adaptive traits of the conifer species, topography, forest structure as interpolated from FIA data, and then this other thing we got at using spatial autocorrelation. And this measurement of spatial autocorrelation is basically analogous to a PCA of variables, but it's a PCA of the spatial autocorrelation variables. And we use those vectors of spatial autocorrelation. And then what I'm focusing on here are these fire interaction variables relating to fire history for reburns, the time, the number of years since the last fire, and the previous burn severity. Oops, hang on. There we go. And it's a lot of words. You don't need to worry too much about it unless you're interested in doing this modeling yourself. But the long and the short of it is we used random forest modeling to make predictive models of burn severity. And we were making models for unburned areas that had just burned once and reburned. So we used a final parsimonious set of predictors for both models so we could compare those results. So what do we find? For reburns, previous fires really matter. And the biggest and most important predictor is this gray bar here is the time since the last previous fire. The other predictors that ended up being really important were these spatial autocorrelation variables. And these ones were measuring spatial autocorrelation at really large scales, as well as this FRS, which is the fire resistance score. This is described and provided in a paper by Jen Stevens and his co-authors. And it's available for, I think, all the Western US where there's conifer forests. And this really ended up being a good proxy for the bioclimatic variation in species composition within our study area and was a very strong predictor in our models. So really what we have here is a strong fire-on-fire effect and then these proxies for large-scale bioclimatic gradients. So let's dig into this just a little bit more for some context. Going from low fire resistance in subalpine fir forest to high fire resistance in ponderosa pine forest, we really see this inflection at this fire resistance score of about 4.9. And for context, to give you like a species specific context, that's the difference in like the in the Douglas fir rating versus grand fir. So Douglas fir versus grand fir in terms of the species traits. And so we really have these two fire regimes within our study area. Within this low fire resistance, higher severity fire regime, we see a strong inflection after about 14, 15 years where high severity becomes much more likely, a bit of a flip of a switch. In contrast, in the dry, higher elevation forest, we see continued resistance to high severity fire lasting over a longer time period. The one other thing we can see from these biplots of multiple variables is that in places that had really low burn severity, which are right here, if it basically didn't burn in the first fire, we find that it's more likely to burn at high severity in the second fire. And so what that really is telling us is there aren't persistent fire refugia on the landscape. Instead, there's fires interacting with other fires over time based on their previous fire severity. So to just draw the conclusions from this, the highlights for this fire severity piece is that within this ecosystem, we have strong negative feedbacks between initial fires and subsequent burn severity. And resistance to high severity, especially in the higher elevation forest, lasts for at least 14 years. And then there's continued resistance to high severity in the lower elevation forests. And if you want to know more about pre-fire and post-fire treatments on severity, or fires in long unburned areas, take a look at the paper. Now, the second part of this joint fire science funded research that I took on with our team was to look at how post-fire management influences forest canopy structure over longer time periods. So really over time for that post-fire management to also allow for some post-management succession and structural development. With the data that was available, we were able to look at 4 post-fire treatments. It's really 3 treatments, two of which are that are sometimes occurred in combination. Harvest after fire, this mostly was salvage logging, but because of the way things were coded in the FACS database, it may have included some harvest for some other purposes. Harvest combined with post-fire planting, and prescribed fire. The harvest occurred immediately, well, within a short time range after the fire, 1 to 5 years. And the planting or prescribed fire occurred 1 to 15 years after the fire. Our LIDAR data was from much longer than that, after the treatments, up to 32 years. For those of you not familiar with LIDAR data, the data you get back from the sampling consists of a point cloud. And for this talk, I'm going to use 4 metrics to describe what happens within that point cloud. One is the cover, which is the canopy cover, which amounts to the percent of returns above 2 meters. The dominant height, so the height of the 95th percentile of returns. And then these 2 measurements of canopy cover within the lower strata, the percent of area with canopy cover and the percent of pixels with canopy cover. Hang on 1 sec. No, please. Sorry, I've got a kiddo at home. Okay, so what did we expect to find? We predicted the long-term effects of post-fire treatments to be either a compound disturbance, so a harvest only would be a compound disturbance, or harvest and planting would be a compound disturbance, and so would prescribed fire. And then accelerated succession would occur when there is planting. And so for compound disturbances, we'd expect that there'd be decreased cover and decreased dominant height. And for accelerated succession, we'd expect increased cover in the lower height strata. To use this large scale remote sensing data to assess the impacts of treatments, we basically created our own control impact design. So we had LIDAR data from all of the treated areas where LIDAR was measured, and we matched that with burned controls that were untreated from the same LIDAR acquisition and usually the same fire year. We had to flex that a little bit in the case of prescribed fires to 2 years before or 2 years after. We used pairwise dissimilarities, so like multi-dimensional space of AET, so actual evapotranspiration, climatic water deficit, and previous burn severity as measured by RBR to match cases and controls. If the pairs were really poorly matched, we threw them out and didn't assess them. So we ended up with this set of well-matched cases and well-matched controls. Okay, so I want to walk you through how we compared these visually. And thanks, Nick, I see that 5 minutes. To match, these are our cases are in purple in these distributions, and our controls are in yellow. So there should be a little arrow here. There we go. Oh, 1 step too far. Okay, and so for this top line, these are harvests, and these are harvest treatments in the purple, and the yellow is harvest controls, and these are showing the continuous distribution using kernel smoothing over the bioclimatic and burn severity variables we use to match them. So we're going to start with this, and basically this is showing how well matched our cases and controls were over the whole distribution of our sample. And what I want you to take home from this figure is we ended up with pretty good matching, not perfect, but pretty good for the harvest, planting, and planting treatments. The plantings were really great. They really matched up in terms of these bioclimatic and burn severity variables. The prescribed fire just had a smaller sample size, and they did not end up being matched quite as closely. So keep that context in mind, and also that the burn severity within the cases of prescribed fire ended up being a little higher. The other thing to see here is that each of these treatments did occur within a different burn severity and climate space. And we'll come back to that point in just a minute. So we're asking, is the peak of the case distribution to the left or right of the control? If it's to the left, the treatment had lower values, and if it's to the right, the treatment had higher values. And so what does that come out in terms of our predictions? And in many cases, in terms of compound disturbance, we did not find what we expected. Harvest did act as a compound disturbance and decreased the amount of live tree canopy over time. But the other treatments, harvest and planting, did not have that effect. And planting had an effect, which might mean that there's something different going on within these planted areas. And we'll go further into that. In terms of accelerated succession, we found that yes, harvest and planting seem to accelerate succession by having greater cover in the lower height stratas, but for planting only, which is on this line, there really was very little difference between these cases and controls. And we didn't see much evidence of much biomass or lidar returns in these lower strata areas in the planting only areas, which was really surprising. So what's going on with the really different effects of planting by itself versus harvest and planting in combination? We think this is related to the bioclimatic space in which these are taking place. Planting alone was occurring on more drought-stressed sites, which made us think there could possibly be regeneration failure, especially where there were few seed sources. So we dug into this a little bit more, just looking at only the high severity observations. And within high climatic water deficit areas, we really had low cover, whether it was planting and harvest or planting alone in those areas. So what we're finding evidence of that hopefully someone can go confirm in the field in some future study is regeneration failure in these dry, drought-stressed sites. So take-home results from our study is that we had 4 treatments, and they were really implemented in different climate and burn severity conditions, and those things impacted the resulting influence of post-fire treatment on forest structure. Harvest-only treatments simplified canopy structure by removing likely some trees that otherwise would have survived. And planting-only treatments were concentrated on high drought stress sites and did not seem to be showing recovery of forests. And that is all. I want to give myself at least 1 minute for questions, if possible.
Thank you very much, Alina. I am checking the Povak. I don't see any questions. If anyone wants to contribute one, now would be a good time.
So this is Pepe. Can you hear me?
Mm-hmm. Hey, Pepe.
So there was no effect on climate. You would think that climate would be a driving factor, but you found that wasn't the case, huh?
In terms of the fire severity?
Yeah, the first part. Yeah.
Yeah. You know, there was a weak effect within long unburned areas. And there was a big effect of fire weather, and that came out in fuel moisture results within the long unburned areas.
Oh, so fire weather was important. Okay.
Yeah, and even then, I would have expected to see a stronger signal from wind and stuff, like just knowing this ecosystem. And I think part of it is still just the scale of the weather data is not high enough to really capture what's going on at the scale of like the fire effects we're measuring. So I do think a little bit of the issues with the weather data only having fuel moisture come out was just that we still have a scale mismatch with what we're really, with what's going on versus what data is available.
Okay, thank you.
Yeah, let me see.
I think I took care of it.
Okay, thanks, Nick.
Oh, yeah.
Okay.
All right. Thank you very much, Alina. That was excellent. So we're just going to move right along. I'm going to be giving the next talk. I'm affiliated again with both Alina and Derek Churchill, who will be giving a talk later, and Andrew's talk. We're all part of this sort of New Fire JFSP funded group. Here, I'm going to be talking about post-fire regeneration. So as we all know, our landscapes are undergoing a tremendous amount of change right now, and wildfires in particular are impacting at an unprecedented amount of area, at least in our recorded history. And as a result, a lot of the landscape is in a state of recovery from disturbances. And these, the forests of our future are sort of developing right now. So one, can we learn from these ecosystems about how they're responding to this influx of fire? And two, can we incorporate these lessons into post-fire recovery efforts into forest development in areas that will be changing in the future, that will be challenged in the future? And so just start off with, there's been a lot of recent research in post-fire regeneration. Camille Stevens-Rumans and Penny Morgan had this nice review in 2019. And what they found was, that there are a lot of factors limiting to regeneration here in the Western United States and elsewhere, obviously. But, things like distance to seed source, burn severity, moisture stress, increased temperatures, repeated disturbances, specific topographies, and other competing vegetation. And what they found, in very broad terms, in general, regeneration was most challenged really at those dry, low elevation sites. But if you'll notice where these fire footprints are, where these studies were, they're mostly in the Southwest, California, and the Rockies, and not really much in this northeastern or northwestern part of the country, where the new fire projects sort of was conducted. And a lot of these reports were done sort of less than 10 years post-fire. So really, we have a sort of a missing geography here, and we wanted to better understand sort of these long-term stand dynamics processes. So not just short-term regeneration, but sort of how does regeneration occur over the long term? And just a note, since this publication, Caitlin Littlefield had done some work in the tripod fire, which is within our study area as well. Our results largely align with what she found there too, which is reassuring. So specifically, we were looking at regeneration 15 to 30 years post-fire. So a long time period for regeneration to sort of establish and grow. We were looking specifically in the Okanagan-Wenatchee and Colville National Forest. You can see up here. This is the Okanagan-Wenatchee, and this is the Colville. It was a factorial study design. We looked at 2 fire severities, moderate severity and high severity. We looked at 2 managements, sort of post-fire salvage without planting, and then a no management. So no kind of management after the fire. And then we looked at different forest types, so dry mix, moist mix, and cold dry forest. So these are sort of our factors, our strata. And then the last kind of modeling we did some species level modeling. We did some regression modeling to sort of identify the environmental factors that were driving the observed regeneration densities across the study area. And so here's just a quick overview. You can see the fires happened, from 1988 to 2003. We did our field work in 2017, so you can see the number of years since fire. And you can see they're well distributed across the Colville National Forest, the CNF, and the Okanagan-Wenatchee. And about 150 of these fires occurred prior to 2000, and about 100 after, and for a total of 248 plots where we measured the trees, regeneration and overstory trees. And so what we found was that regeneration was abundant. We found a median a density of around 4,000 trees per hectare in regeneration. So regeneration here is anything between less than 4 meters in height. And large regeneration between 2 and 4 meters in height was around 700 trees per hectare. So, pretty good. There was a lot of variability among the plots, but this is what sort of we found in general. And then we had a low incidence of regeneration failure. So only 2% of plots had no tree regeneration, and about 15% of the plots had less than 350 trees per hectare. Here's just a quick breakdown of the different species. And so this is the percentage of plots that each of these species was found in across this, our 248 plots. And where they were present, this is what sort of their density. So this is the 25th, 50th, and 75th percentile. Obviously these are highly skewed distributions. So we're using these medians and stuff. So Douglas fir was found, we found regeneration over almost all of the plots. Douglas fir was found pretty ubiquitously. Ponderosa pine, less than half of the sites. Lodgepole and western larch and Engelmann spruce kind of rounded out the species mix. And you can see they're sort of occurring at fairly high densities. So to kind of cap off what we found kind of at the plot level, dry forest, again, as Camille and others found, dry forest generally had the lower densities. high severity fire increased regeneration densities, but that was largely driven by lodgepole in our sites. Salvage harvesting had kind of a very variable influence. It did increase regen densities, but that was mainly on the Colville, and it's possibly due to how we kind of selected our plots. In general, it's common that after salvage, they go in and plant to sort of help regenerate the area. And we specifically sought out those sites that were not planted. It's because we're interested in natural regeneration. So we selected unplanted sites, which might have had naturally high regeneration following the harvest. So we might have actually kind of went to areas that were naturally high in regeneration, which may have upped the densities and for that strata of our study. And we found significantly more regeneration on the Colville versus the Okanagan-Wenatchee, and I'll get into that. So the next analysis we did was this sort of species level correlative modeling. So our response variable here was regeneration density, and we did it for all species and then for individual species. And our predictors were things that we measured in the field, so residual overstory size and density, and then things like climate, post-fire weather, national forest membership, years since fire, and then our different study strata. And we use this generalized additive mixed effect model. The mixed effect here was national forest membership. And so one thing to note, we did see these differences in the two different national forests. And here we're plotting kind of the climate normals, mean annual precipitation on the y-axis and mean annual temperature on the x-axis. And the dots here are study sites. So Colville is in blue and Okanagan in yellow. And you can see that in general, Colville was a little cooler than the Okanagan, and it had kind of a tighter range of precipitation and kind of like in the median level of precipitation. So Okanagan had much more of a broader precipitation range and was warmer, while Colville was cooler, and we'll see how that kind of played out. So these are kind of response curves for here's all species combined model. And these are the main variables that came out. We have climate normal, mean temperature and precipitation, post-fire, so these are percentiles, post-fire temp and post-fire precipitation, aspect, slope aspect, and then overstory basal area, QMD, grass height, and distance to seed tree. Distance to seed tree is going to show up a lot. We, like many, have found that the further away you get from a seed tree, the lower the densities and the higher probability of regeneration failure. So on the Colville National Forest, densities declined with increasing mean temperatures. So if in blue here we have a specific effect of this variable mean temperature on the Colville National Forest, but no effect on the Okanagan-Wenatchee. Where you have gray, there's neither a significant effect on Colville or Okanagan-Wenatchee. Where it's red, they had the same effect and it was significant. So you can see, a decline in regeneration with mean temperature. As the temperature goes up, regeneration went down. And then for post-fire temperature, this was kind of interesting. So Colville here was the cooler of the two national forests, and as post-fire temperatures went up, you actually saw an influx of regeneration. And on the Okanagan-Wenatchee, which was warmer, you see a reduction in regeneration densities with increasing post-fire temperature. For both cases, the more precip following the fire, the better the regeneration. And then we see this, one other thing I'll note is the QMD here. You can kind of see this U-shaped, and you'll see this again. The U, we think this is sort of related to this 4-meter cutoff that we had for the regeneration. So where regeneration was ample, you could see, this sort of, there's probably a lot of overstory in, sort of 4 meters, but just above 4 meters. So there's this influx of smaller trees and regeneration. And then as overstory QMD increased, you see this larger, more regeneration underneath. And then real quick, I'll just go through a couple species here. Ponderosa pine, we see a precipitation response, particularly on the warmer Okanagan. So there's sort of this sweet spot for precipitation. It wasn't really affected by post-fire weather, but you see this sort of steep decline in regeneration densities as you get further away from seed source. Douglas fir, this is our most widely distributed species. You see a slight increase in densities, particularly in the Colville, and the warmer you get, but there's no effect of temperature in the warmer Okanagan-Wenatchee. And for Okanagan-Wenatchee, as precipitation increases, you see increase in regeneration densities. And again, you see this sort of different effect of post-fire temperature, where warmer post-fire temperatures on Colville led to higher densities, and lower temperatures led to, higher densities in the Okanagan-Wenatchee led to lower density regeneration. I don't know if I said that right. And then finally, Western larch, you do see a temperature response. Here, post-fire temperature was really the main driver, and it was specifically in Colville, which is where the majority of Western larch was found in our plots. And so this was sort of really responding to post-fire temperature. So if we kind of step back real quick, so why all the regeneration? Well, we think what's going on is that these plots experience favorable post-fire weather. So here are the percentile weather conditions 1 to 3 years post-fire. We developed these percentiles using a 50-year history of weather at specific to each of these sites. And so what you see is really low climatic moisture deficit, high precip, and low temperatures. So this is 1 to 3 years post-fire. So you have this really nice environment for trees to establish and grow. And what we also found was the further back in time you went, so the longer the time since fire, the cooler the temp. So there was a correlation between time since fire and this percentile temperature. So the plots that we measured here had a much longer time to develop, and actually developed under more favorable climate or weather conditions. And so we wanted to kind of, again, take a further step back and look at other studies that have looked at post-fire regeneration. And again, we're looking at some of Camille Stevens-Ruman's work. She looked at 485 measured sites across the Rockies. You can see the distribution here. They covered 52 wildfires, and she had a really long temporal record too. Some fires were more recent, but she still had some fires that occurred, very long ago, decades ago. And she found just significant decreases in post-fire regeneration in the 21st century. So after 2000, they saw this really strong signal where there was a decline in regeneration. It was driven by these higher annual moisture deficits. And so dry forests at the edge of these climate tolerances were prone to these post-fire conversions. So what we did was took Camille's data, who was nice enough to give it to us. And so here again, we have mean annual temperature on the x-axis and precipitation on the y. And this is kind of the climate space. So all of her plots are in orange, and our plots are in blue, the Colville, and yellow, the Okanagan-Wenatchee. And we subset her data to match our sort of temporal extent. So it's the further back fires from I can't remember, 1980. Well, anyway, went up to 2003 anyway. And we matched, and then we matched the kind of climate envelope. So here is our 95th percentile kind of climate envelope. So we subset our data and her data to kind of match both time and climate. And so her kind of subsetted data is up here. And you can see that, so this is temperature again. So the warmer the temperatures, the more, here the X's are where she found zero, total regeneration failures. And then red is where you have sort of low regeneration. So you can kind of see this temperature gradient moving from cool to warm, and where the warmest sites had the highest incident of regeneration failure. And that is a sort of a sample space that wasn't really sampled too well in ours, but where we kind of approach that temperature, the sort of 8 degrees, 7.5 to 8.5 degrees Celsius, we're not seeing quite that failure. We don't really see that trend here. And what we think is going on is, again, this climatic moisture deficit. Here are our plots versus her plots. We had much lower climatic moisture deficit 1 to 3 years following the fire. And similar, we had lower temperatures and increased precipitation. So it's really that window following the fire that we think is really contributing to this abundant regeneration that we found. So to sort of cap this off, again, we found abundant regeneration 14 to 29 years post-fire in the Eastern Cascades. The abundance was driven, we think, by favorable post-fire weather conditions, and these conditions will likely occur less frequently under climate change. So we're expecting to see tremendous change sort of moving forward, because some of these species, or most of these species, are have sort of climate windows that they prefer, and we're likely going to exceed those in the future. But the thing is, can species take advantage of these temporal windows of favorable conditions? Clearly, these favorable conditions are going to be less frequent in the future, but they still may exist, and there's still going to be an opportunity for species to establish and grow following fire. But the big question is, how often is that going to occur and co-occur with fires? So there's a big question mark there. Regeneration was more abundant in salvage areas, but that may have been the way that we chose our sample sites, where sufficient natural regeneration occurred following the salvage harvest. Regeneration was more abundant on high severity fire patches, but that was largely driven by lodgepole pine, particularly on the Colville. And then, despite ample regeneration, we still did see these species level tolerances that drove local abundance. So species were still responding to gradients in climate, post-fire weather, topography, and overstory tree conditions. And distance to seed source is likely going to be a key variable, obviously, moving forward. So long-term studies, we think, are key to our understanding of these prolonged stand dynamic processes. But again, they suffer from the discrepancies in the climatic context. So the climates that they experienced in the before 2000 are much different than they are now. So the question is, how relatable are our results going forward? And again, we expect to see less regeneration and shifts towards these drought-tolerant species in the future. But there's also sort of the flip side, is that there are opportunities to sort of foster the development of early cereal conditions that we know were more prevalent prior to in historical period, and anyway, there's opportunities to sort of divert management away from areas that we know are going to have less ability to regenerate. And with that, thank you very much. Oh yeah, and all of these results are published in our Ecosphere paper that you can see here. And I can put the link in the Whova. All right, well, I pulled an Alina. We got 1 minute for questions. I will check the Whova. Okay, cool. No questions. Anyone want to offer one up?
Hey, Nick, this is Jens.
Hey, Jens.
Hey, just real quick, I was trying to remember from your paper, I think you did stratify your plots by distance to seed source, but if I remember correctly, most of your plots were within, I think the average distance was like 60 something meters to a seed source. So did you ever do an analysis that subset the data, filtering out the lodgepole pine heavy plots and just looking at the plots that were farthest from seed sources to figure out, if there were some if that's where you were seeing your regeneration failure?
Yeah, well, the only thing we did do is, use distance to seed source as a predictor in those models, and those were species specific, and all of them really showed a decline in species abundance with distance to seed source, and the sort of anyway, the trends matched very well to other studies that Camille and Penny show in their 2019 review. So thanks.
Sure.
All right, next up we have Morris Johnson from the U.S. Forest Service Pacific Northwest Research Station in Seattle. Take it away, Morris.
Okay, good, thanks a lot. Okay, so I'm Morris Johnson. I work for the PNW Research Station in Seattle. And so today my topic is going to be passive or active management, understanding short and long-term consequences of changes after large-scale wildfire. So my talk is going to be a little bit different from the previous talks. It's going to be less on the results, mainly because of the process that I'm working with. I began my career with Forest Service systems, so my research is basically tailored to help managers understand some of the problems that they're dealing with. And so I would just like to acknowledge the other co-PIs on this project. So Maureen Kennedy at the University of Washington and Sarah Harris. But before I go any further, I would also like to acknowledge my collaborators from all the different national forests if your name is on this slide, I appreciate you responding to my comments. Responding to my emails and my constant pestering. So I've had lots of collaborators from all across different national forests. And so I'd like to begin my talk with, after the fire, what's next? That's really the big question that a lot of managers have. And so I was recently on IDT team on the Minnesota National Forest, and we were on this panel, basically giving an overview to U.S. Representative Huffman and Ann Carson, the forest supervisor for the Minnesota National Forest. One of our comments in our opening presentation was, there are a mix of perspectives on how to manage post-wildfire landscapes. And I was thinking, well, if anyone can make that comment and have the experience, that would be Ann, because within the last basically 3 years, 97% of the Minnesota National Forest has burned. In 2018, when I first began working with the forest, we had the August complex. So the ranch fire burnt 166,000 hectares. And then just in 2020, we had the August complex, and it basically burned over 1 million acres, and it burned across the Minnesota National Forest, Shasta Trinity National Forest. And so after you have these large wildfires, you can look in some of the local newspapers and you can see opinions across the gamut, right? And so I was thinking about, what are the perspectives that Ann is talking about? And really, the perspectives are really, there's really two perspectives, right? Those who support, active management or salvage logging, and then those who do not support salvage logging. And those who support salvage logging, they have their reasons why they support salvage logging. Number one is there's the opportunity to recover economic value of timber, right? And then, farther down the list, there's an opportunity to reduce, a potential rebirth. And then those who are against, salvage logging, we say, there's research out there that says salvage logging reduces natural regeneration. Salvage logging is detrimental to wildlife habitat. All of these are legitimate claims, right? Now, from a management perspective, you think about the opponents or the proponents. Really, we are talking about passive management or active management. And that is really what happens after these large wildfires. The managers have to decide, okay, well, what would happen if we don't do anything, right? What are the ecological consequences in terms of, if we don't do anything, how are we going to achieve our overall management objective for that area in the future, right? And so working with some of the data from the complex in 2018, we basically did some simulations, right? And we just said, okay, if we don't do anything, this is what FES, if we don't do anything over time, the model is predicting that we will have an increase in woody field loadings. But if we do some type of management, that's what this other lines represent, then we can see that there's a change in woody field loadings. And then all of these different alternatives give us a pathway to meeting our management objectives. Now you take that same figure and you overlay it with protected climate change, and you think about, if you have the increase in this case, dead woody field loading, and you have a reburn, right? That's what in 2030, because if you look to the left, you can see that Mendocino National Forest has had lots of wildfires. So that's basically the burn history of the forest. And so if you have this increase in woody field loading and you have a repeat wildfire, it's more likely you're going to have fire effects that are not going to help you get to your overall management objectives. And so, after these large wildfires, I basically reach out to these managers and say, okay, what are we going to do in terms of, are we going to actively manage? Are we going to do passive management? And so if they are going to do active management, obviously there's a process that we have to go through. So we have to do this NEPA. So if we decide to do active management, then we're going to go to NEPA. I, try to get myself invited to join the IDT team. And on the IDT team, my job is really there to do monitoring. So I basically, Andrew Larson in 2013, they came up with this excellent paper, Making Monitoring Count. And overall, basically, if we are going to address some of the issues between active versus passive management after these large fire events, we need to basically start monitoring now. And so On the IDT team, my job is really to say, okay, if we're going to pursue active management, we need to address those who are not in favor of active management. So how do we do that? So I work with the managers and say, okay, if we want to pursue this, we should set up a way where we can actually quantify the effects of doing salvage logging, in this case, and the effects of not doing salvage logging. And really, we should basically include this in the purpose and need. And so here's an example. This was the first study that we did. I guess a lot of researchers worked on this. Eric Knapp from the PSW. We had a whole bunch of us. We, this was our freshman year, and we tried to get this one to work, but unfortunately, we didn't get any trees cut. So if you look in the purpose needs on in the EIS on Eldorado National Forest, you would look and see that line item 6 says promote scientific research. Plumas National Forest, after the wildfires, you see line item purpose and need number 3. There's some reference to addressing this research question about active or passive management. Mendocino National Forest, just recently, August Complex, same thing. Shasta Trinity National Forest, August Complex, like I say, August Complex was a pretty big fire, so it burned across a couple national forests. So all of these national forests, I was on the IDT team as a member, and basically we wanted to look at, set it up so we can address some of these questions. And then way back in 2017, we also implemented this monitoring project on the boards of national forests. And so really, the study objectives is basically establish a long-term replicated monitoring project to look at the long-term and the short-term and long-term effects of doing salvage logging on fuel succession and potential fire behavior. And the short-term obviously would be if we install the plots and we actually have the salvage logging to happen, that would be the short-term. And then the long-term would be basically, what I will talk about later, is looking at what would happen to fuels over time in the control units. And so we basically, after we identify our planning area, we would basically measure the fuels before we do the salvage logging, measure it after, and then we basically set up over time where we can go back in and remeasure over time. So obviously we have research questions, like I say, what is the effect of salvage logging on stand structure, finding woody fuels, and what do treatments affect overall shrubs and seedlings regeneration? What are the effects of herbicide application? This was one we were hoping that we can get implemented, but so far none of the studies that we have implemented have actually had the approval to do the herbicide. And then after some of the previous talks mentioned that after we do salvage logging, there is planting. So we have the study design set up where we can look at what would happen if you do planting, if you don't do planting. And so I've been doing this for a couple of years now. And what I found is that depending on which national forest or BLM land that you work with, some of the opportunity to implement these block designs is limited by the polygons in which we're going to salvage log. So I had to adjust the sampling design. So on BLM land, they usually have some pretty odd shaped polygons. So I had to basically do a paired design where I look at treated and untreated, adjacent untreated. And then some of the areas like BLM also, the polygons are pretty small. So I basically have 2 randomized block designs. So one is 2.3 acres and then one is 5.4 acres, but you don't have to worry about that. I can talk about that kind of stuff later. So an example, Mendocino Complex, Plastic Keller, August Complex. So, this is basically the location within the Mendocino Complex. So initially we start off with the scoping. So our planning area is about 25,000 acres, 25,000 acres. And then these are the initial polygons that we start off before all of the specialists go out. And then we end up reducing it down to, X number of acres, because you have to remove areas that have, a higher percent of opportunity for erosion, invasive species, wildlife habitat, things like that. So after we determine our final planning areas, obviously I would say, okay, well, if these are the areas that we're going to put in the NEPA document for that we're going to propose to do salvage logging, then I propose to do a randomized block design. So randomized block design in this case is, I think what we did in this project, 5 blocks. And so random, for each block has 3 cut units. And so we randomly assign 1 of 3 treatments. So RX1 is, control unit. RX3 would be full salvage in this case. And then we have a RX2, which would be a partial salvage. And so each cut unit is 5.4 acres as in this example. And then each 5.4 acres has 24 fixed area plots. And we do snags and seedlings, fixed area plot, a nested fixed area plot, and we do 4 brown transects in each plot. And they will also look at shrubs and non-woody vegetation. Shrubs and non-woody vegetation. And so I mentioned that we also have this partial harvest. And so the partial harvest is depending on what the forest is interested in analyzing. So for the Mendocino National Forest, I think on the August complex a couple of years ago, one of their environmental groups was interested in what would understanding what would be the effects if we did do salvage logging, but we had a limit on the DBH of the tree that we can remove. And so they wanted to say they wanted to thin all trees up to 53 centimeters. And so on this August complex, we actually implemented that this summer, and that is we thin all trees up to 53 centimeters, and we have full salvage, and then we have a control unit. Boise National Forest, they had a target residual stand density, and then the Plumas National Forest, they were a little bit more adventurous, and they wanted to look at salvage area retention. And so salvage area retention in this case, so each of the 5.4 acres has 15 subplots. And so if you look at this partial salvage logging, so we randomly assign, we randomly will select 4 or 5 of the subplots. And then from those subplots, then we will actually go in and mark all those trees as, mark everything within the subplots, and we will remove those. And then we basically have a variable density post salvage logging prescription. Now, the reality is, in the planning phase, this all sounds nice, but the reality is the NEPA process takes a while. On average, it takes us probably like a year. And within that time frame, a lot of the timber value, decreases. A lot of the large wildfires that happen in California, in Oregon, and Washington, they also burn across a lot of private timberlands. A lot of the private timber companies, they also own the mills, and so they are able to harvest their timber before the Forest Service is able to get through the NEPA process, and therefore a lot of times we're not able to sell our timber, and therefore we're not able to actually get the salvage logging treatments cut. Like on the Pioneer Fire, I have 5 blocks with lots of control units. But on the Coville National Forest, a couple of years ago, we actually were successful in on the Coville triplets, we was actually successful in implementing 5 blocks. And then we actually had some big wildfires that happened like this summer, and we're going to repeat it on in 2022. But even though the plots were not cut, this data will still be valuable because we can basically use FFE to make projections over time of what we think the fuel loading is going to be in the future. And then as we go back in periodically to remeasure those, we can basically calibrate the model to say, okay, the FES predicted the fuel loading to be X. And then we can actually go back in and actually remeasure the plots, and then we can calibrate the model. And so here are just projections over time for the El Dorado National Forest and Mendocino National Forest. And you can see, obviously, time since disturbance, you can see that there is an increase in dead woody field loadings. Now, the FES model does not predict any shrubs and non-woody vegetation, which is a major driver of fire behavior. But this type of data is a good planning tool for fire managers. And so this is, if we are not allowed, if we are not successful in getting the area salvage log, this would be our outlet to get this information out to the managers. But we were, so like I said, on the Covert National Forest, we were able to actually get some salvage logging done. And, overall what we found was, salvage logging increased. The 1 hour and the 10 hour woody field loadings, it was significantly different than compared to the control unit. But overall, in terms of affecting fire behavior, there was, it really wasn't significant because they actually did a pretty good job in salvage logging with whole tree harvesting and removing fuels. And then the results from the COVID tribe plan was really about the same. There was a significant increase in the 1 and 10 and 100 hour field loadings. But it wasn't a really significant increase in terms of affecting fire behavior. And then obviously compared to comparing the control unit projecting over time to the treated area, if you do not do salvage logging, obviously you will see an increase in woody field loadings. And that increase in woody field loadings or the passive management would probably prevent you from obtaining your management objectives. And then I think that should be it.
Great. Thank you so much, Morris. Leave it open. Let's see, the Hoover, anyone? Nope. Okay, anyone have a question for Morris? Okay. Well, we have 2 minutes. I just wanted to mention that we have one more talk in this morning session from Derek Churchill. We are coming back after the break with 4 other talks. So I encourage everyone to come and revisit us again. I guess we'll just hand it over. Derek, are you there? I know he is somewhere. Derek, where are you, bud?
Hey,
I'm
here. Okay.
So yeah, next talk is from Derek Churchill. He's from the Washington State Department of Natural Resources. Go ahead, Derek.
Okay. Well, yeah, it's great to be here. A lot of great talks in the conference, and so my talk is part of the New Fire project that Andrew led off with, and Alina and Nick have talked about. And the part that I'm going to focus on is we evaluated 4 separate wildfires and looked at the sort of landscape level work that they did and how that then feeds into post-fire management. Before I start, I just wanted to acknowledge Morris. I actually worked with him on the Colville project he just mentioned, and it was amazing because he just showed up that summer after the fire with a whole study plan, and we're able to really implement this project in one summer. It was just a great partnership between science and management on that to make that project happen. So anyway, just quick background in my project on this talk here. I work for the Washington State DNR and on this 20-year forest health strategic plan for Eastern Washington. And this is a really ambitious effort to do a lot of treatment, all kinds of different treatments to restore and adapt our fire-prone landscapes, fire-dependent landscapes in Eastern Washington. And so we have these, we've identified these planning areas where we really try to focus our treatments. And for each of our planning areas, we do a landscape evaluation where we identify the overall amount of treatment need, as well as prioritize locations. And then we work with all the different landowners to help implement as many of those treatments as we can as quick as possible. And so we found when we do these landscape evaluations that we typically landscapes need to treat 30 to 45% of the landscapes with some kind of treatment to get them in really resilient condition. What we've also found, however, is that these fires, all these yellow circles here, a fire has occurred in all of those planning areas at some point in the planning process. And so, you know, nature isn't allowing us to go through this nice linear rational planning and implementation process. The fires are happening midstream, and, you know, we can no longer be surprised when that happens. We have to expect it and really integrate it into the restoration work that we're doing. Because we'll just never catch up if we get really bogged down every time there's a fire, and that's what often happens in these processes. And so again, these papers Andrew mentioned, and others mentioned, just came out. So I'm going to be talking for the main part of my talk about the results from this paper, which looks at 4 wildfires in these 4 sub-watersheds in eastern Washington, northeast Washington. And then at the end, I'm also going to talk about, similar to Morris's talk, kind of a live management application on the Colville National Forest as well, where we're putting these sort of principles to practice and trying them out. So we have 4 fires again, and they span a range from large patches of high severity in Benson Creek all the way to predominantly low severity with some moderate and high in Scatter Creek. And just so you know, when we look at this analysis, we're just looking at the fire effects within the sub-watershed boundary, the black boundary, not the whole fire perimeter. And then we are including the unburned portion of the watershed as well. And so, you know, we looked at this overarching question of, are fires moving landscapes towards more climate adapted conditions and resilient conditions? Obviously, there's still a lot of questions or thinking that, well, wildfires are doing good work, and they often do some good work, but there's often negative consequences. And so we really wanted to take an objective look at both of those. And so we evaluated fires based on these 4 landscape restoration principles. Are we restoring the patchworks of forest, woodland, and shrubland? Are we shifting the amount of forest structure in the right direction and pattern of forest structure? Are we sustaining the large and old trees? And then are we shifting species composition, which I won't talk about today? And so the methods for this analysis, we use, as Andrew mentioned, photo interpretation. So for each fire, we have pre-fire imagery and post-fire imagery. And we do photo interpretation, delineate polygons, and take the attributes. And then we compare those with this historical data set of imagery from the 1930s to the 1950s from the Interior Columbia Basin Ecosystem Management Project that Paul Hesburgh and many others worked on. And so the way this works is, for a particular watershed, like this little red watershed here, you have a set, these dark green subwatersheds that have similar climate as that. And so you take 10 to 15 of these historical watersheds that have that imagery, and that is your HRV, historical range of variation. And then you take another 10 to 15 watersheds from warmer and drier conditions, these dark orange watersheds, and that forms your FRV, future range of variation. So it's a kind of space for time approach to FRV. And then, so you're going to see a number of these graphs for each metric. We have a range here, right? So this is the amount of open large tree forest. So we've got a range here of the HRV from those 10 to 15 watersheds, and a range from the 10 to 15 warmer and drier watersheds. And here's our current fire, our current state of the landscape, and then we have a fire, and it may move it, into the range here of the two, or it may overshoot, right? And so looking at our first metric here, again, I'm going to start with the Scatter Creek fire, which was predominantly low and moderate severity. You can see that we did restore down here this patchwork of forest, woodland, and shrubland. And we reduced the amount of forest up here. You can see this is the percent of the landscape right here. The mean patch size is over on the right here. And so we moved the forest actually to within the HRV. We increased the amount of woodland, increased the amount of herbland. And so really this fire is sort of pushing this area more into that future range of variation in terms of that. And you can see that here, you know, in this photo. This photo is actually not from this watershed, but gives you the idea of this kind of patchwork of forest and non-forest. It's obviously a highly dynamic situation, a lot of regrowth, future fire, so this will move around a lot over time. And then looking at forest structure here, again, the fire did some good work of increasing the amount of open canopy, large tree and medium tree open canopy. So when I talk about forest structure down here, we have these large closed, large open. The large is the overstory diameter, and these are these breaks here. And then the cover, the closed and open, is this threshold of 50% canopy cover. Anyway, you can see here the fire definitely decreased the amount of this medium closed and increased both the large open here and the medium open. You know, we're still kind of in the low end here, but our mid-range, there's more room to go for the future, but you know, it did move things in the right direction here. Again, as Andrew and Morris talked about, you know, there's more. This is a great first entry, these low and moderate severity fires. There is more work to do here, often more green trees to thin, as well as a lot of future fuel there. So now moving into Benson Creek, here we kind of had an overshoot where, you know, the fire converted this big green patch of forest here, converted it to this really large patch of herbland. And so, you know, it's pretty obvious in the data, or just from the photo, but you see it in the data where we've, you know, reduced the amount of forest here, really reduced the patch size, and then increased the amount of herbland, you know, well outside of the HRV and FRV, as well as the patch size here. And so, you know, this is just sort of quantifying the obvious, but it does really show that these large high severity patches are pushing these landscapes into different states, basically outside of our historical ranges of conditions. And so 70% of the landscape is in one giant patch, of which is now predominantly herbland. And so this fire also really reduced the amount of large trees. And you see all the dark green over here, that was large closed, and it all burned up, as well as some of the large open structure class. And so again, you see that in the data. We're now towards the lower end of the large closed. And so again, we're okay in terms of the HRV, FRV, but we lost the opportunity to shift that to large open, right? It's going to take decades or centuries to regrow those large trees. So that's a lost opportunity there. And then a couple examples from the West Fork Channaway here. Focusing in on landscape pattern. This watershed before the fire was fragmented, and you can see here, this is a cumulative patch size distribution, and so all of the little greens are the HRV and the orange are the FRV, and so the solid line here is the pre-fire landscape, and it basically shows you there is we don't have as many as the medium and large patches as we did in those historical landscapes. We're at the fragmented end of the envelope there, and then the fire actually pushed us outside of the envelope. It further fragmented the landscape, and basically in this unburned portion of the watershed in the southern half, it had been fragmented from past management. And then the northern half is pretty dissected topographically, and the fire really, you know, further accentuated that, broke up the large patches that were there. So again, it compounded past fragmentation. Then the other problem with this fire with particularly the large closed here is that now the remaining large closed is in the wrong places biophysically, and so. Right here, we had a lot of large closed that all burned up in the fire, and it was located in the most climatically favorable locations with low moisture deficits on these north-facing slopes, right? Meanwhile, The remaining large closed is in these much drier locations, which is unlikely to be sustainable into the future from both drought and fire. And so this landscape isn't set up well to sustain that large closed forest. And so we kind of put all this together in this principal components analysis, where on the x-axis down here, we have a variety of tree size and canopy complexity variables. And then up here, we have canopy cover on the y-axis. And just to show you, these are our structure classes and where they fall in this ordination space here. So again, down here is open, low canopy cover, low tree size and complexity, canopy complexity. And then over here is our large closed and small closed up here. And so then we can drop in for Scatter Creek. These are the kind of the average condition for those HRV watersheds, and there's a hole around there, and then the FRV. And so you can see, the HRV is has higher canopy cover, greater tree complexity than the FRV, but there's quite a bit of overlap there as well. And then we can look at over here what the fire did, and it, as we would expect, fire reduces canopy cover and also tends to reduce tree size and canopy complexity, particularly the high severity fire. And so it pushed us in that direction. But we're still well within the FRV, although we're getting towards the low end on some of the canopy. Well, we're still within the FRV there. But then we look at Teanaway, and here we were already outside the FRV for canopy cover before the fire, again from that past harvesting, and it pushed us down even further. And the same thing with Teanaway, where we actually started with Benson Creek. That was the big high severity fire. We actually started with too much. We're high on the canopy complexity, but the fire pushed us all the way down to the very edge here. And so what's likely in these two watersheds is that future fires are going to keep pushing them down in that direction. So really shifting them from a forest dominated landscape to a non-forest herbland, shrubland landscape with a lot of young forest, and be in a kind of a high severity cycle. And they won't have enough time, most likely, to regrow back into those envelopes. Versus Scatter over here has more options. And so, our conclusions here, I'm not going to go into these in detail, but in a nutshell, wildfire is a blunt tool in these fire excluded, untreated landscapes. And all of these fires were uncontained fires that happened during warm, dry conditions. These were not moderate fire weather fires. These were big fires. That moderate and low severity fire is a good first entry. Again, high severity fire can restore those patchworks of forest and woodland and grassland, but it can also homogenize them if the patches are too big. And then wildfires can often compound pre-existing departures. Sometimes they better align we found some evidence that they can better align the landscape with a topographic template, but other times they did the opposite. And then really we concluded, again, from all our new fire research, that intentionally planned treatments with strategic wildfire response, letting wildfire do good work when you have the right conditions, that's really going to set us up better for future climate and wildfire than these large wildfires. Okay, so I'm going to, this is pretty short here, talking about this sort of live management application that we started this fall. We're still working on with the Colville National Forest. The Walker Creek fire. This is in the same neck of the woods, right up here in this pink here, by our other areas. And we're, again, working closely with the managers on the Colville, some of the same people I've worked with a long time, or Morris worked with. The Colville is great because they have a lot of management capacity. They're a highly functional forest, and they also have a whole assortment of mills that actually want small logs. And by small, I mean less than 14 inches at the butt end. They don't actually want large logs, so it's an ideal situation for post-fire management. So this is a relatively small fire, but had some large patches of high severity here. And so what I'm talking about here is really focused on short-term actions. So salvage sales and planting that are going to happen this winter and spring. There's obviously longer term actions as well that we can talk about. But what we did here was really that short term. And what the forest wanted was, can we help them sort of establish the ecological rationale for treatment and prioritize their treatments? And this was kind of a dry run, if you will, or trial run to see, can we build more of a system and rationale for future fires? So I'm not going to go into this, but just so you know, we took some of the principles that Andrew presented on and boiled them down a little bit for this project, and sort of had this framework for the high severity areas and then for the low and moderate severity areas. And then we developed some prioritization criteria and whatnot. We did do a quick and dirty landscape departure analysis. We had pre-fire lidar structure classes, and then we used the fire severity map to infer post-fire structure classes. And from that, we're able to get these departures right here. And so I'll just show you a few maps here. This was our high severity, both identifying where treatments might be possible, again, based on the high severity, the burn severity maps. And then we used higher soil burn severity, distance to seed source, and drier veg types to prioritize areas. And then they went out, or so I should say, it was kind of a process where they actually were laying out all these units kind of as we were developing it. And so we compared kind of the units they chose for both salvage and planting with our prioritization. And, there was some certainly overlap in the locations, some overlap in the prioritization. What we really learned is that boiled down to operational restrictions and also NEPA restrictions, that this big area in the dark gray is far from the road or steep slopes, and that really limits where they look to do actions. And so when you take that out, we have pretty good coverage with our prioritization. And so the moderate and low severity prioritization, again, we feel like fire did this great first entry. We have an opportunity to finish the job here, and we can do it in a way that pays for itself and do it quickly, so we get at least some of the landscape in a really fire resistant condition sooner than later. This one was a little harder for them to implement for a lot of different reasons. It's hard to do with NEPA, to do a green tree thinning with the categorical exclusion. They had to use past NEPA in some places. The current ways to do post-fire management, people just think high severity, that's what they assume with salvage. They don't really think about treating these moderate severity areas. So only one unit kind of fell out here, which is in our sort of mid-range of our prioritization. But again, a good lesson learned there. So yeah, just in conclusion here, we've learned a lot through this process, primarily that managers are really eager for sort of moving away from this economically oriented view of salvage to more of a ecologically based post-fire management. And these analyses need to happen really fast. And that we learned you really have to customize the prioritization for each area, each fire. But there's a lot of challenges to doing this, both operational, sort of cultural. We have a long way to go here, but I think we're, some exciting first steps.
All right. Thank you so much, Derek, and everyone who contributed to this morning session. Like I said, we'll be back again after the break with some more talks. So I hope everyone comes and joins us. And I think now I throw it back over to our fearless producer, Anthony. Thanks, man.
Thank you so much, Nick. Thank you to all of our speakers for sharing your expertise with us today. This session will be available in Whova, our conference app, within 2 weeks after the Congress ends. We're going to take a 20-minute break before beginning our next set of breakout sessions at 3 p.m. Eastern Time. There are 6 special sessions, each featuring a great lineup of multiple speakers and their topics. And we also have our first of the 2 virtual field trips. To choose the one you'd like to join, use the agenda tab to the left of your screen and click sessions. You can also click subsessions for more details about what to expect. To join the session offering Spanish and Portuguese interpretation, be sure to select the session titled Wildfire Simulation under Future Climate Change, Methods and Applications. Thank you again to our speakers and enjoy the rest of your day. Bye-bye.